I will future. Not open twice. This is not needed. Okay, I can send it down. Nobody connecting. Okay, I think we can start. And what I have for today, before we speak a lot about all kind of things, but most of them were, let's say, stationary regimes. But there is one moment left unattended are transients in general. We saw free oscillations, yeah? One of the transient kind. But what should I do when I need to find free component of the transient regime? The general idea, what we have anything. It is not mandatory what it's electrical circuit. It can be mechanics, it can be anything. But we have, let's say, some switch on, and we have some, let's say, voltages, currents and time, and so on. First idea to make calculus, to make all this feasible, we separate resulting regime or mode in two parts. One, so let's say simple thing, we charge condenser. Can we charge condenser? I have an M. It connects via resistor to condenser, and this is the form of it will be like this. This one will reach the E voltage, and this line can be written as E1 minus A power. So idea what this common voltage, this whole voltage, can be separated in two parts. Let's say free component plus infinite time or enforced component, also stable. So at the, let's say this is when time is infinity. This one is enforced or infinite time component. And between this transient process is a free component or components. Enforced or infinite time component, it's easy to find. It requires basic knowledge of electrotechnics. But what about free components? Direct solution of such problem requires what? To solve differential equation. I don't like solve differential equation. Do you like to solve differential equation? Few people like that. One of the approach to find this free component is let's say connected, or it's derived from idea of Laplace transform. If you study in United States, you will hear about Carson's Heaviside transform. But here we mostly rely on Laplace transform. We heard about this. Laplace transform allows us to operate in some, let's say, magnificent Laplace space where such a mass operation like find of derivative or integration are represented like a simple division or multiplication, like simple mass operation. So idea of this technique, so-called operator technique, is not to solve a transient problem as a problem in time space, but to solve it as a problem in Laplacian complex frequency space. You may also find another version of designation. It's the same, no difference. We will not operate with time function, but with the images in the Laplacian space. Solution itself in Laplacian space is much easier than in time space. But there is one problem, and it's problem how to get results. We will have our transients as an image. We will have nodal voltages. We will have branch currents as a function of complex frequency. We need to get them back in our time space. It requires inverse Laplace transform. Usually, for such operation, tables of functions are used, or problems, you can find this problem under the name of Mellin integral. Mellin problem. It's solved by the technique developed by Cauchy with residues. But for problem of physical nature, for electrotechnics problem, for problems of mechanics, for example, behavior of control system, something like this, you will see what real system has a limited energy. If system, real, with limited energy, is subject to some transient, some influence, for example, heat or, I don't know, someone put a brake pedal on your car. It's a disturbance. A real system with limited energy have, if the system is stable in some degree, we will see process of decaying oscillation or decaying process. Real dissipative system has tendency to decaying process. For such process, where real time, real frequency regime exists, we can apply a technique of numerical inversion of Laplace transform. Krolov conducted this technique. It's a way to solve Mellin integral numerically. If you read Latvian, find this nice book, on the page 333, you will find detailed description, but I'll show it in brief if I will be able to connect to my One second, I will open. It's a short document. 1 second, I will. Yeah, I will make it public. Yeah, do we see it? I hope yes. So here's a short word document. Where, what can we see? We need to solve this. It's a Mellon integral. Common way is to use residues, but we can go numerical way. So substitute, use the substitution to, what's the idea? Idea is to represent an Laplace transform in such form as shown, and later substitute this inner function with a Fourier role, where sine series will have a coefficients like this, but they can be found from other side. Direct calculus of this sine coefficients is not possible, but we can find them from the, let's say, from the opposite side, but we will need to use a kind of base point or base net of equally distributed points with a specific step between them. This will allow us to find first two elements of the integral as a combination on the basis of, actually they are binomial coefficients. So I combination from two of m elements. So this row, this kind of series will be feasible, and we will get a link between sine series coefficients and the values of the function in Laplace domain. This allows us to find these sine coefficients and perform needed Fourier transform. In reality, this means what we will need is a set of partial regimes or partial modes at a discrete frequencies, defined by the step of points we used. One only moment, this thing grows very rapidly. It wasn't used before because it requires computer with a quite wide integer. You need at last double integer to use this technique. Okay, here is the block diagram of this technique. Of flowchart. This will allow us to perform numerical inversion of Laplace transform. You can check this example. It was used to find a temperature increase of cowplet. What cowplet? We have a shielded fiber optic cable under the high voltage line. Line wires are metal coupled with the shield. So question was to find temperature increase of the shield. And here is a small example. Now let's use this technique in more general way to solve a transient problem. I have created, this document is available through the e-learning system. I have prepared a demo. 1 second, I'll switch. I have prepared a demonstration. I will switch back to my scope. What is demonstration? Network, not easy to solve, real. DC source, switch will go in. This is grounded. On the secondary side, I have resistor, capacitor, and ground. And these coils are mutual coupled. Such network isn't easy to solve, really. Switch on the couplet network. How can we solve it? First idea. We need to conduct schematic in Laplacian space. General idea, when in classic electrotechnics, you use an what kind? Reactance. Here we will use special resistance. For elements, simple resistance. Electrotechnics theory, what we will use? Resistance. In Laplacian space, it will be resistant. Coil. What should we use? J omega A. Yeah? PA. Replace image frequency with complex frequency. I left the space intention. Capacitor 1 against omega C. Yeah? 1 against. And mutual inductance, couplet coils. Omega M. PM. What kind? It will be, if these are for diagonal elements, I'll show it in red. It's M to O. Capacitance. Why I have left this space? This one base law in our world. What's energy do not appear from nowhere and do not disappear nowhere. For Laplacian space, we need to ensure energy conservation law. This means what we need to have additional elements to represent a state at the transient, at the moment of transience. For coils, it will be zero. For capacitors also M minus 0 divided. Trust no one. Where's my yeah, of course. Yes. Of course. So it will be in sequence with coil. This is okay. And this one will be in sequence with my capacitor. Yeah, that's good. These elements will ensure what we correctly introduce border condition or see state of the elements what can store energy at a time moment when transient occurs. For metal inductance, if you substitute with the T network, also should be accounted. Yeah. My network, I can repeat it, is simple. For the first test, I have selected a network with the zero border conditions. Before switch is activated, there is no current and there is no voltage. So I don't need to think about border conditions. Now I need to draw this network as it would be in Laplacian space. E divided, it's a DC voltage. 1 coil. I will split a coil into, better say, 3 parts. The blue one, self, and red one will be motor. On the opposite side, again, it's self, motor, here is my network, prepared for Laplace L1. Next step, this one will also be ground, this will be base node. Now I will use a simple topological analysis. I need to specify number of nodes and assign numbers and directions to my branches. Yeah. This will be node 1 and this will be node 2. When I solve the system, I will get voltages there. Okay. This is branch 1. I need to select directions. I need to select direction. This is branch 1. This one is branch 2. This one is branch 3. And this one is branch 4. I have assigned numbers to branches and directions. Without directions, nothing works. What should I do now? Next, I need to represent these schematics to my computer. First, I will need a topology matrix. I will free a bit of space for me. Topology matrix, node, branch, and conduction rule is if branch inflows in node, I should write -1. If it flows from node, I should write 1. And if there is no connection, 0. For my case, how many nodes I have? 2. 1 and 2. Basic node is not accounted. And first, second, third, and branch. Here is template for my first incidence matrix. What can we say? First, branch inflows in number -1, 0. Second branch 1, 0. Third branch leaves second 1 and here 0. And also leaves second, so here is 0. Here is my first incidence on network topology matrix. Connections, branch nodes. If you heard about first Kirchhoff's or Kirchhoff's current law, it's a matrix of Kirchhoff's current law. Network topology. Second one, I will need a matrix of resistance. Its form branch and branch. It's a rectangular matrix. Main diagonal of this matrix is filled with the branch own resistance, or better say impedance. And other elements are neutral. Do we have neutral elements here? Yeah, we have. Pair. In my case, 1 second, I will bring elements. This one will be 26 volts. First resistance is 200 ohms. The second one is 60. Capacitor 1 microfarad. And for coil, this coil has own resistance 17.5 ohms and inductance 82.77 millihenry. This one resistance 23.45 ohms and inductance 234.5 millihenry. Metal is standard 100 millihenry. So, resistance matrix for the first branch. 1, 2, 3, 4. 1, 2, 3, 4. One, 200 ohms. Number 2, it will be 17.5 plus P 82.77. Self distance for the third 23.5 plus P. Hey, what I'm doing? Self is 23.45. Right. This is wrong. $35.9. Yeah. $35.9 plus P 204. And for number 4 it will be 60 plus we will have here 60 plus 1 against P 1 A minus 6. Okay. And that's not all. I have a magnetic coupling between second and third network. This means what at position 3, 2 here, 3 and 2, it's here. I will need 1 and the same 2, 3 here. Also P multiplied by 0, 1. one moment, machine. One moment, I will show it. This one is no longer needed. 1 second, I will show it as a program code. Come on, machine. Yeah. I will need this is something. I will see where's the problem. I will need to calculate regime at a different values of the complex frequency. To make it, let's say, to make code to make a good code, I pack network as a function like sine and cosine. So what I'm doing, I'm defining a function of a complex frequency. Network calculus will be packed as a function to make it easier to use. What do we have here? Value of EMF, value of resistance capacitor, and self-parameters of this nice standard inductor. Nice standard inductor with known parameters. So here are self-parameters of primary and secondary inductor coil. It's a standard metal inductor, so here is the 0, 1. Next one, this is topology matrix. Next, these two MS, it's from Latvian mathematical skaits, number of nodes, number of branches. That's Zaru skaits. The first one is number of nodes, second one is number of branches. This one, small matrix, EMF organized as by branch. I have only one branch with EMF, so I'm putting EMF there. Resistance matrix. I help myself. I use a Dirac operator to form a diagonal matrix. First resistance, self of the primary side, self of the secondary side, and last one, it's 60 plus capacitance. Last one, these two are marked in red on the table. Since I need inversion of this matrix, I use built-in inversion function. These two. These two elements are to prepare nodal admittance matrix. I will solve system, machine will solve, but okay, I will solve system with the method of nodal admittance. Its equation is recursive. If not, we will need this vector. It's a base node admittance vector for any case. It's a sum where from 1 to number of nodes from 1 to number of nodes. But this is current source vector. In our case, also equals to 0. We don't have current sources here. EMF matrix, resistances, potential. But what about this? It's called nodal admittance matrix, and it's equals to M inverse resistance and transpose nodal matrix. It's easy. So here, where here you can see I have prepared nodal admittance equation, and I solve it, sorry I'm lazy, with built-in Gaussian technique. It's a method of the Gauss. Quite popular. I use built-in. I can use, in fact, I can use any linear equation solver capable to work with complex numbers. This row yields me a branch current. It's from Latvian ZAR branch, so it will yield me a branch current. And I return from function what? Node voltage and branch currents. This part describes a network, and it will be called multiple times. Main program. This is, maybe I will, a bit. This is, not to confuse, it's a number of approximation members. It's an integer number of approximation members. Maybe not to confuse with the network matrix, I will switch from M to AM. It's a member of approximation. I will have 15 points. Simulation will take 10 milliseconds. Within 10 milliseconds, I will have 3,000 points. Actually, this sets precision. How many points? I cannot perform continuous calculus. I will calculate some limited number of points. In my case, I will use 3,000. This parameter also sets precision. It's a step of the frequency. It's a bit trick. You need to select it somewhere around 2p divided by t, 220p. Bigger yields a faster calculus, but less precision. Number of variables, how many variables I use, and how many voltages. It's a total number of time signals from them to our voltages. This point is at the moment I use a network when there are 0 conditions before I switch For this case, initial values of all variables are zeros. So I simply fill them with 0. And now I call my function. I will need to call it multiple times. Here I realize this idea of creating, let's say, of obtaining Fourier decomposition coefficients step by step. And in this point, I will recreate a time values from the factors achieved. This will be an array of factors. And the only thing I need to do, I need to draw results as a voltage or current. Let's try to run it. What's going on? Line 97. Sorry, it's an approximation member. My mistake. Yeah, I would like to save and execute. Okay, what I got? Pair of voltages. Can you see them? Okay, I'm showing online. People see currents. This one. All currents in time, and here are my voltages in time. Maybe I can. I will try to show them on screen. Here are calculated voltages and calculated current. But who can trust this chart? How can we trust something like this? Somebody pushed a button and somebody get something. Let's try to get them in reality. Sorry, I will connect you. Let's do. Here is battery, 26 volts. Here is first resistor, second resistor, capacitor. Invisible. These adjustments. Yeah. Here is my capacitor and my not ideal. Oh, this one is better. Yellow line is a first node voltage, primary, and the blue line is a voltage on the secondary coil. Something familiar? What can I do? I can. One moment. is here are calculated. Oh, wait 1 second. Where are calculated voltages? I'll need to switch. Yeah, this voltage are calculated. See some oscillation to it. We use numerical approximation. Here is calculated primary voltage, here is calculated secondary voltage. 15 volts, decay in 6 milliseconds. It's the same real. Each division is 2 milliseconds. 1, 2, 3, 4. And amplitude 5 volts in each division for blue line. 5, 10, 15. Similar. Reality looks like here how it's here they are. One moment. I will take a look at them. For online, I'm comparing calculus results. Yeah, calculus results. The first one is yellow line, the second one is the blue line. I think they are quite close. Okay, what we can do next? We can try this connection. This was simple, isn't it? What kind of network can we use? Let's try something like this. I will add 1000 ohm resistance just to close net. This will be R3. Well, this is ground. This will become branch number 5. This is branch capacitor. This is node 2 and this is node 1. Something like this. Disconnection of the network. Previous current direction was like this. Yeah? One moment. Where is my... Let's try to do it. I can close this and this, and I can switch here. 1 second. What should we after? Let's put 3 equals to 1000. Now, should we add additional branch? I'm not sure. Why? We can live without it. We just count it as a first one. So this means what I will just add plus L3. I will have, at the first moment, I put a 0 here. But that's not correct. Where is my mistake? What should I add? At the time 0, this part disappears. But what should I add? I need to represent energy of magnetic field of self-inductance of this coil. Current was before. And if current flowed before, magnetic field of coil stores energy. I need back from 0 plus. You understand? Okay, what it was? So I'll need to put an EMF, it's branch number 2. Yeah, this one is second branch. And it is, what should I write here? I need EMF multiplied by P, or, okay, simple EMF, this means what I need to remove this, divided by, what's on the flow of it? It's resistor 1 plus third resistor plus self-resistance of the first coil. It is 17.5 ohm. Ohm law, DC regime before. Oh no. 1 second. Why I'm adding F3? I don't need it. I need current flows only through first resistance and the self-resistance of the primary coil. 17.5. If I turn this nice clock upside down, I'll see what active resistance resistance of the primary coil is 17.5 ohm. And its inductance is 82.77 millihenry. It's a self-parameter of the so here I have and I need it to multiply. It's a current. And I need, where is my mistake? Where is inductance? Where is my nice table? On a page 333. L E L. L E L. It's L. So I need to multiply this by self, and this is self. You know, it's looks stupid. L self 1 equals L self 1 equals now here will be now I think it's more clear. Second and here, and this one goes here, and now this goes here, and this goes here, and this is not needed. Yeah, I think this form is more. So, you see, I put in the second branch EMF representing energy of magnetic field of the coil. For the, in theory, if there would be, let's say, a charge of capacitor or pre-computation for current, pre-fault current, in the secondary part, I should put the reflecting sources also there, but I don't have them, so this one is, this should be satisfactory. Let's try to run it. What I got? Voltages and currents. Currents do disappear quite rapidly. Voltages. This one disappears quite fast. Maybe I will try to simulate it in short wave simulation time. Let's simulate for 2 milliseconds. Yeah, what's within 2 milliseconds? I will make it visible to viewers. Here are voltages. You see short spike in negative and stable. Secondary part, short spike up and then it should oscillate for in different currents, short spikes in different time scale. Let's say 12 milliseconds. Close these windows. Run. In different times, short spike and oscillation. Let's try now. What we can do? We can try to not to simulate it, but get it real. This is theory, yeah? Let's see what happens. I have this nice release switch. And what we got? Maybe I need to change scale of the yellow signal. Not ideal. Can you see? Short spike in negative and very slow oscillation. KTC. Short spike going negative for the primary, and for secondary, the computation is not ideal. I cannot see. I cannot release switch without vibration. I'm not a robot. But you can see short spike in lines on the primary side and decaying oscillations on the secondary. Should be up to 300 volts. How deep the spike goes? Looks quite deep. One moment, I will start at some 20. How long it's? 1 millisecond. It should be 10. Let's take, for example, 20 milliseconds. Calculate. Voltages. Can switch. Sorry. voltages in different scale. You see, short spike and negative, and I can play with sigma to make this more linear, but it's a problem of, in fact it's because we use numerical solution based on Fourier law, it's bit oscillates. Again, incarnation of Gibbs paradox. This one. And here you can see voltage up and oscillates down. Smaller resistance. Not a... Hey, come on. I tried not a 1000, it's 500 ohms. Short spike. It's oscillates, but it's different. And I'll try to get tail of it. It's 500 ohms. 1 second. Where is my... Let's try to get the same parameters. F3 500 go. How deep this spike goes? Quite a bit. 1 second. I need to switch. Hey, come on, I'm switching. Here, calculator. Looks familiar, isn't it? Real. This one is yellow, and this one is blue. Quite close. Big difference in this. This one oscillates. And this is what I have, 4 milliseconds, 8, something like 10 milliseconds. Where am I? What a simulation time I have set? 20. Okay, let's switch to 10 and go. Here are voltage in shorter simulation. Close, close. I do not control currents. Here it is. Hey, you, come back. calculated. There is a big difference. And reality. I have big difference. I'm not accounting capacitance at the primary side, and my switch is not ideal. This computation is not ideal, but you can see quite close. So with the help of this technique, it is possible to solve transient problem. You will find this yields you a free component. And first, you calculate with traditional theory of electrotechnics. And yes, it works. What should I do? Maybe play a bit with it's smoother, but and simulation time. Yeah, this one is very good, except one tiny moment. You know where my mistake is? I made one mistake, and its mistake is I did not set a 0 voltage for the first node. I left it 0, but it wasn't 0. It wasn't 0, that's why I saw these oscillations. For the first node, zero state. Was it 0? No, it wasn't 0. It was 26 multiplied by 17.5 and divided by 17.5 plus 200. Sorry, it's my mistake. Let's take shorter simulation time to see the difference. Shorter simulation time, only 1 millisecond. it's my mistake, and here is effect. See, it's smoother. And its element, yeah, it's a first. Let's go from the 0. It should not be 0. Let's very it should not come from 0, while in this scale it's, yeah, it's not coming from 0. Let's see, earliest. The very beginning of the process. Yes, it's small positive voltage. My God. It comes from the small positive. Currents and my voltage. Be it more precise. Be it more precision. No. No. I can left like this. Yeah, it was my mistake. I should set a 0 whereas the same current. Actually, the same should be done for current, and what element it is? It's a branch number, current number 2. It's number 4. I should do it for currents also. Zero conditions. Yeah. This is to set a 0 condition. Sorry. Where is the division? And yes, you can see current starts from, in the second branch, current do not start from 0. It should start from nice. Now it's okay. 0 conditions. Yeah. I need to set them. Or nothing works. Okay. Boom, 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 boom. You saw it. Recursion to chart. oscillations, decaying. That's what we get. Okay, I think I have a feeling it's enough for today. And of course you said put these examples in a learning system, yeah? 1 second, I will do it.